So we've been doing stoichiometric calculations, which include mole-to-mole conversions, mole-to-mass, mass-to-mole, mass-to-mass, any of which are fair game on your quiz. Your quiz for period 6 only will be on Monday, so you actually get the weekend, although I don't think you need it because you should have a pretty good grip on it at this point. The other type of stoichiometric calculation you can do involves density. So you may be given the mass or moles of one substance and asked for the volume of a gas. That will involve that you use the density of the gas. Alternatively, you can be given the volume of a gas and you can determine either moles or mass of the other substance. So both types of conversions will involve density. It's a matter of where you put density and whether you use density as is or if you use the reciprocal of it. So we're going to walk through a series of 3 problems, and then there are a couple of problems on your classwork that correspond with it. Now, while this is not assessed on the quiz, it fits with what we've already done, and so I think it's good to cover it here. You will see it on the second quiz for this chapter. This chapter has 2 quizzes and then an exam. So density we know is mass in grams over the volume, typically in mils, but sometimes in liters. If they ask for the volume of the substance at the end and they don't specify the units, whatever the volume unit in the density that's given is what you should use to make life simple. If you need to do a conversion, please remember that 1 liter is 10 to the third or 1,000 milliliters, because that can come in handy too. Okay, in the example shown, it says in space shuttles, the carbon dioxide that the crew exhales is removed from the air by a reaction within canisters of lithium hydroxide. So we know we exhale carbon dioxide. You can remove carbon dioxide by reacting it with lithium hydroxide. You can have lithium hydroxide in canisters on such a space shuttle. On average, each astronaut is going to exhale approximately 20 moles of carbon dioxide daily. And we want to know what volume of water should be generated when 20 moles of carbon dioxide react with in excess of lithium hydroxide. The density of water we know is 1 gram per mil, and we will use that. In these types of problems, the density will be given, and that will allow you to convert either from mass to volume or vice versa. The first problem's a little simpler than the other 2 because it's 1 less step. But this requires that you understand the previous conversions that we have discussed. So we want to know the volume of water that should be produced. That's what we're looking for. And we have 20 moles of carbon dioxide. The equation is given. I'm going to rewrite it here. And these problems are going to be very long. We have carbon dioxide reacting with lithium hydroxide to generate lithium carbonate and water. And then we will balance that equation off, and we're ready to use it. We're told that we have 20 moles of carbon dioxide, and we want to get the volume of water. The density of water is 1 gram per mil. Since the unit in the density is grams per mil, we're going to solve for mils of water since they didn't specify otherwise. Whenever you're given moles, the first step is always the mole ratio. We have 1 mole of CO2. We want to get to water, and the balanced equation also shows that we have 1 mole of water. Here's my mole ratio. Whenever you're given moles, you always start with the mole ratio. In the next step, we need to convert from moles of water to the mass of water in grams. We know that 1 mole of water is equal to 18.015 grams of water, the molecular mass of water that we've done previously. So this you're already familiar with. You can see the cross cancellation of units. Here's the new piece of the puzzle. Here's where we're going to use the density factor. We know the density of water is 1 gram per mil. If I have grams of water here, then grams of water must go here. The number that goes with grams is 1.00, and that's per 1 mil of water. So this density factor, if you're solving for the volume, is the reciprocal of the density. And then you have 20 times 18 is 360 mils of water. That's the volume of water generated. By each astronaut daily. All right? So all we did here is add an additional step. If you let your units drive your problem, you will be successful with this type of calculation. The second problem is very similar. It says if there are 325 grams of lithium hydroxide present to react with an excess of CO2. The excess of CO2 does not configure in this calculation. Again, we want to know the volume of water that should be generated. Same type of setup, one additional step. Here we were given moles, here we're given mass. So basically there's a step we need to insert right here to get to moles. So again, this is where really setting your problems up carefully with units and substances is critical, because all of a sudden we had 3 steps and here we're going to have 4. So in the first step, we've got 1 mole of lithium hydroxide equal to its mass in grams. Now if you're the kind of person who really just needs to keep going, worry about the formula masses at the end. You can see the cancellation. Now you're at moles, you want to get to the other substance. We've got 2 moles of lithium hydroxide in the balanced equation to 1 mole of water. So now we got to the moles of the substance we want. We can get to the mass of the substance we want. And how do we go from mass of water to the volume of water?
But
Go ahead, Faith.
you have to put, wait. Oh wait, yeah, put 1.00 grams on the bottom and 1 milliliter on top.
You got it. So this is the reciprocal of the density. And this piece is coming off the periodic table. Lithium hydroxide is 23.9479. So you have 325 times 18.015 equals divided by 23.9479 times 2 close, and that's going to be 122 mils. And you're going to see some of these on your classwork. We're going to do one more, but it's going to be completely backward. It's not hard. You just have to let your units drive your problem and you'll be fine. If you have good factor label method skills, you'll be golden in this section. The last problem says the reaction that causes cake batter to rise involves the production of carbon dioxide from sodium bicarbonate when the latter reacts with an acid such as acetic acid. What mass of sodium bicarbonate is consumed? That's what we're looking for, highlighted in yellow, when 7.14 liters of carbon dioxide gas is generated. That's my given. The density of carbon dioxide is provided as well. Incidentally, that is the exact reaction that you ran in the lab last week, where you generated a gas and you saw bubbles in the flask. In regard to this equation, we've got sodium bicarbonate found in baking soda and acetic acid. There's acetic acid in vinegar. You're going to generate sodium acetate, a salt, water, and carbon dioxide. And the air pockets you see in bread, cupcakes, cookies, etc. is due to the CO2 being released. Is that balanced? Yeah, it looks balanced. All right, well that makes life easy. We're given 7.14 liters of CO2, and what do we want to get to?
Sodium bicarbonate mass.
We want the mass of sodium bicarbonate. And in the lab next week, you will be reacting sodium bicarbonate with hydrochloric acid. You'll generate sodium chloride and you'll mass out your product. Okay, how is this problem different from the previous one? You're starting with the volume in liters. So previously, when we were solving for the volume, we used the density factor last. Here we've got to use density right away. Now the problem told us that the density of carbon dioxide is 1.10 grams per liter. And they gave you liters, which makes it easy, because if you have liters of CO2 here, you need it here. And this is per 1 liter. 1.10 grams of CO2 goes here. So your density goes right at the beginning, and you don't need to take the reciprocal since you are getting rid of the liter unit. Once you do this, you're already at mass, and this is going to then be a mass-to-mass problem like we just discussed. So then, let your units drive your problem. If you have grams of CO2 here, you need it here. 1 mole of anything is equal to its mass in grams. The molecular mass of carbon dioxide is 44.009. You've got 1 mole of CO2 to 1 mole of sodium bicarbonate. Cancel, cancel. And what would the last step be? Mole to mass. So you have 1 mole of sodium bicarbonate to its mass in grams, again off the periodic table, and that's 84.0059. So you have 7.14 times 1.1 times 84.0059 divided by 44.009, and that's going to be 15.0 grams of sodium bicarbonate. And again, if you let your units drive your problem, you should be highly successful with these types of calculations. So these calculations involve volume, so you will need to use density, either straight up, if you're going from volume to mass or moles of a different substance, or with the reciprocal if you're given mass or moles and you're solving for volume. And 5C in your classwork is a problem that involves density. There's another one, but you're not quite ready for it yet because it involves limiting reagent. So for your class, whereas the other classes are quizzing tomorrow, your class will quiz on Monday, and then we will begin limiting reagent, which helps put the whole chapter into perspective. We'll work on that. We may have a little carryover for Wednesday, lab on Wednesday for you next week.
So this is on Thursday.
This type of stoichiometric calculation involving volume is not assessed on the first quiz. I wish I did, but I already ran the quizzes off. It is assessed on the next quiz. So what you want to do now with the remaining 13 minutes is work on the classwork through 5C. Get a good beat on it. If you need help, please, please ask. I'll come around and see how you're doing with it. If you're not feeling great about it, I'd be sure to do it by tomorrow. So if you have any issues, you can pop in the morning and get them addressed. You should have a much better understanding of stoichiometric calculations at this point.